Let's explore the periodic table, how it's organized, what do the different columns and rows mean, and where to find specific categories of elements. While you do have a color-coded periodic table as a lecture tool, you should become familiar with an unmarked black and white periodic table so that you can easily identify elements or regions as needed. The general structure is set up as a grid or a table. How convenient! Not all periodic tables are set up this way. There are some that are spiral, some that have longer rows, and many other designs. For most purposes, this general structure of rows and columns works pretty well. The specific periodic table that we will be using in this class is a design that I constructed in 2019 and updated in 2020. Believe it or not, it took a lot of research to investigate how to portray the pieces of information because there isn't a standard presentation. The rows, which are numbered from 1 through 7, are called periods. We'll use these values more extensively when we talk about orbital diagrams and electron configurations, but for now, you can use them to help locate certain elements or regions. The columns, which are also numbered, are called groups. The first set of numbering, 1 through 18, is a designation recommended since 1988 by the International Union of Pure and Applied Chemistry, or IUPAC, to avoid ambiguity in which group is being referenced. The second set of numbering using Roman numerals is an American designation. You'll notice that this numbering excludes the center part of the periodic table and was a way to differentiate between main group elements, which have the Roman numerals, and transition elements, which do not. As the definition of transition element continues to evolve within the scientific community, this American numbering no longer aligns completely with its original intent. Despite these changes, the Roman numerals do prove to be useful, and they are allowed by IUPAC, so I've included them here as supplemental numbering. The first classification we'll consider is metallic behavior, and whether an element is classified as a metal, nonmetal, or metalloid. The easiest way to distinguish these three categories from one another is as follows. First, locate the 7 metalloids. Start by realizing that the metalloids begin with B. Move diagonally to silicon, then start the staircase, down to germanium, right to arsenic, down to antimony, right to tellurium, and down to polonium. That's all there is to it. Once the metalloids are docked or labeled, we can identify elements to the left of the metalloids, except hydrogen, as metals, and elements to the right of the metalloids, plus hydrogen, as nonmetals. Some of the more recently discovered elements are not yet categorized, and so they are not color-coded. Identifying metallic behavior is straightforward, as long as you know where the metalloids are, and you remember the hydrogen is not a metal. The next way we can categorize elements is by whether they typically exist as atoms or molecules. Most elemental forms are considered atomic, which means they are essentially single atoms. A few elemental forms are diatomic, which means they exist as 2 atoms of that element bonded together. You should commit to remembering the diatomic elements because anything that is not diatomic will be atomic. Furthermore, when you write the element in its diatomic form, you must include a subscript 2, like shown here for hydrogen. The 2 means that this chemical formula is for a molecule that contains 2 atoms of hydrogen. If you are simply identifying an element like hydrogen from the periodic table and are not referencing its atomic or molecular form, then you would just write H without the 2. Years ago, I learned a way to remember the diatomic elements as have no fear of ice-cold beer. I cannot take credit for this mnemonic, as I did not invent it, but it works pretty well. Maybe you have a different way to remember the diatomic elements that works better for you. Whatever you use, once you know which 7 elements exist as diatomics, the rest of the elements are atomic. We can also designate the elements by the state of matter in which they exist at room temperature. solid, liquid, or gas. It's easiest to remember these designations by lumping them together into all or most as much as we can, and then dealing with the differences. At room temperature, the solids are all metalloids, most metals except for mercury, and some nonmetals, which aren't otherwise classified as liquid or gas. When identifying iodine as a solid, be sure to report it as its diatomic formula of I2. There are two liquids, mercury and bromine. When identifying bromine as a liquid, it must also be reported as its diatomic formula of Br2. And finally, the gases, which include all noble gases and the 5 remaining diatomic elements, which should be written with diatomic formulas. The final way we can categorize elements circles back to the metal, nonmetal, and metalloid designations, but now we investigate further subdivisions of the metal and nonmetal categories. The metalloids are still the metalloids. There isn't anything new or additional to learn here. The nonmetals can be described as 3 subcategories: noble gases, which are the elements in group 18 through radon; halogens, which are group 17 elements through astatine; and other nonmetals, which don't have a specially named category. The metals have 6 subcategories. Alkali metals are group 1 elements, except for hydrogen. Remember, hydrogen is a nonmetal. Alkaline earth metals are all of group 2. Transition metals occupy most of the elements in the center part that dips down in groups 3 through 12. You should know that most textbooks classify zinc, cadmium, and mercury as transition elements, but it turns out that these 3 elements and the newer element, copernicium, do not meet the IUPAC definition of a transition element. Other metals that don't have a specially named category can be found in groups 12 through 15. Lanthanoids include lanthanum and all elements from cerium through lutetium. Actinoids include actinium and all elements from thorium through lawrencium. The terms lanthanoids and actinoids were recommended by IUPAC in 1985 instead of the terms lanthanides and actinides, so as not to imply anionic properties. Despite this recommendation nearly 40 years ago, the terms lanthanides and actinides pervade and are used in most American textbooks. More recently discovered elements with properties that are unknown or uncertain are not assigned a color here. I hope this tour through the periodic table has been useful and maybe even fun to help you understand the different ways that we can categorize the elements. See you next time.